So let's take a look at where we left off at, which was, oh, we lost Sergeant Grove. There he is. Okay, we left off with pulse code modulation. We have 3 steps to it. We were just on Nyquist there, talking about 2 times the highest audio frequency is how we're going to get the sample rate. When we look at pulse code modulation, there are 3 steps to it: sampling, quantizing, and encoding. With the first step, sampling, what we're going to do is we're going to horizontally check this signal out. We're going to divide it into 1 second, and we're going to sample that 8,000 times in that 1 second. Now, what does that mean? Well, in that horizontal area, we're going to divide it into 8,000, and then we're going to look at the waveform and hit every one of those pulses in there, and it's called pulse amplitude modulated pulse, which PAM, like the spray PAM, when you get ready to make your eggs, you can go ahead, squirt it in the pan, and there you go. Not Peter Pan, but PAM, the buttery substance for your eggs in that. So when we look at those 8,000 samples, it's a representation of the analog waveform. So when we come over to the second step, quantizing, we are going to put it on what's called a quantization table. Yeah, that's a mouthful, ain't it? Quantization table. Now, with each one of these, you can see how we took from the PAM signal and put it on this output with these pulses. They resemble the analog signal if you were to connect the dots. On this table, we have a positive 127 and a negative 127. Now with uniform quantizing, I use this particular scenario of showing you a graph paper, and you can see that everything's equally spaced horizontally and everything's equally spaced vertically. So you have each step from +1 all the way up to +27 is equal in distance, and same with the negative numbers from -1 all the way down to -127. Now with that in mind, we're going to put the pulses on each one of those. And you can imagine there's 8,000 samples that you're going to put on 8,000 of those equally spaced sections of the table. Now with this, there's 254 steps. What's the calculation of an 8-bit code or 8-bit word? Well, let's take a look. Let's go all the way back up to our area where we had that 8-bit word. And there you have it. There's 8 bits, 1 through 128. If you were to add 1 through 64, 1, 2, 4, 8, 16, 32, 64, you should come up with 127. Well, wait a minute, we're talking about an 8-bit word. Au contraire, we'll get there in just a minute. So pay attention to that and what we're going to be leading up to. So we're still in quantization. Wow, what was the chance of that happening? We have a positive 127 and a negative 127. And with that in mind, we have each one of these pulses is going to fall in an area where they're giving some credence to the letters. In other words, we have this thing called uniform, and the problem with uniform quantizing is sometimes those pulses fall in between the lines. Well, that's not good because you can't give it a point whatever, because 8-bit words don't do that. It's either it's a 1 or it's a 2, it's a 4 or it's an 8. There's no way to get in between those numbers with a decimal point. So what needs to happen? Well, it needs to round up or round down. As you well know, that the rounding scenario or the law or whatever it is called is from Anything from 1 to 4, you round down, and anything that's 5 and above, you round up. But there's a problem. They call these quantization errors. It's all those roundings. Well, with quantizing in a uniform scenario, we got issues. We are going to have a lot of them until we do one thing. When we go from uniform to non-uniform, we still have the same 127 lines in the positive and the same 127 lines in the negative. What changed? Well, with non-uniform quantizing, instead of each line being spaced equally, what they found out is the human voice of the masses. In other words, they went with the masses and they started to squish all these lines together to where they can prevent most of the quantization errors. That's the rounding. Now, as you get closer to the higher plus 127, those lines start spreading apart. And that's because, again, this table is equal. Hey, it's set right here. Here's a 0 line. You got X amount of lines this way and X amount of lines this way. But by varying most of the lines in the middle, in other words, squashing them in, you're able to eliminate most of the quantization errors. You don't correct all of them, you correct for most of them. So by going from a uniform quantization table to a non-uniform quantization table, you are now going with the idea of helping out with quantization errors to begin with. The third step, which is encoding, we are going to take the first 7 bits and put a number to them with the positive or negative 127, but we got to figure out a way to get it either positive or negative to tell it, hey, this is on the positive side and this one's on the negative side. The 8th bit is used to tell us whether it's a positive or a negative number now. So this is the third step. Let's take a look at how they encode it. So what they've done here is they've shown you a quick table from 0 to 5 and 0 to negative 5, and they put it to numbers. So you can see that a plus 2 is 0, 1, and all zeros, and the last number or the last digit is a 0. So anything that's a 0 is a positive number. Anything that's a negative number is a 1. How they came up with that and being able to decide that we need to go this route, your guess is good as mine on that one. I haven't found any information as to why. But it's the engineers that put this together that made the most sense. So here is your 8-bit word on how to encode the pulses that we put on the quantization tables. So it just goes to show you the 3 steps that you had back in block 2, which is now block 3, the PRIC 150s, uses PCM. That's how you get your analog voice to digital voice. Now, with that in mind, how many people out there have used Audacity or even heard of the program Audacity?
I've used it, sir.
You've used it?
Yes, sir.
Okay.
I've used it as well, sir.
Good. So you know what I'm talking about when we say PCM now, because if you were to save your audio file or whatever music file that you had, when you go to export it after you've played with it and manipulated it or whatever, when you export it, you got a couple, like dozens of choices. But the 2 main choices are either a WAV file or an MP3 file. Now, with the MP3 files, that's where you'll see PCM at its best. There's a selection in there where you can view every one of the selections, and I think there's probably about 25, 30. Everything from 8,000 times a second for sampling all the way up to 320K. That's a lot. That's insane. So what does that mean? Well, it means that the more you sample, the better the quality of the audio. But in our wonderful world of communications, we only need to sample the voice. We don't need to go from, most of our music is anywhere between that 5 hertz all the way up to 20K hertz, and sometimes I've seen stereo systems go all the way up to 25K. Most humans can't hear beyond 20. So with that in mind, the more you sample, the better the quality, but you also need more processing power. So when you look at a radio, you don't need that processing power, that much processing power, to just transfer your analog to digital voice and try to do all the other stuff with it too. So it doesn't make any sense to use all that processing power just to get a high quality audio. You just want to communicate. So that's the reason why we keep it at a low end. And I use the Audacity for my Christmas music because I sync my lights to music. Yeah, I'm one of those guys that does the circus act with the lights at Christmas. So I have a transmitter, sends it out. You can watch the lights blink to the music. So fun stuff. I enjoy it. Next up, we have something called a frame period. So we've changed now the analog to digital to what is it we need to do with frame periods. Well, when we take a look at a frame period, that is all these channels, and what we need to do is we need to find out how long it's going to take from point A to point B to sample all of those. Now, you can see it says in this particular definition, it says the time it takes for one frame to occur. That one frame is how many samples did it take for that 8,000 to go through all those frames, all right? Or one frame. So you take the mathematical equation, you don't need to know the mathematical equation, you need to know what the definition is. The mathematical equation proves our point. So we have frame period is equal to the reciprocal of whatever your sample rate is. So in our case, or frame period, so we got 1 over 8,000 frame periods, and it comes out to like 0.000125 seconds or 125 microseconds. So that's how long it takes to do one frame for, that's the time it takes for one of those frames to occur. We have another one called pulse modulated sample period. Now this one is the time it takes to sample one channel in any given frame. So what we're doing here is, here's our frame, here's 24 channels. How long did it take to do, let's say, channel 3? That's what we're looking at. How long did it take to sample channel 3? So in our case, we use the standard of 24 channels in a multiplexer. That's the standard. There are less, like I told you before, the FCC 100 had 16, and there's others that might have like 50 or 60. There's crazy amounts out there. But, again, we look at the standard here. 24 channels in a multiplexer. So what we do is, in order to get PMSP, we take the frame period and divide it by the number of channels in there. Now, it's pretty simplistic. So if I have 24 channels and it took me, in our case, 125 microseconds to sample all of that in that one frame period, how long did it take me to sample, let's say, channel 3? In our case, by the time we divided that into 125 microseconds, we end up with 0.00000528 seconds, or 5.28 microseconds. That's pretty doggone quick. So let's review. Frame period. It took us 125 microseconds to do that one frame period. To look at channel 3 and how long it took us 5.28 microseconds. Ridiculous, isn't it? Just wait till you get into the faster ones. Then it gets even smaller. So that's what a PMSP and a frame period, just remember the definition on that and how they got it. You know, is a frame period bigger than a pulse modulated sample period? Yes. Pulse modulated sample period is looking at just one channel, whereas a frame is looking at everything. So we looked at general multiplexing terms this morning, data relationships, types of multiplexing, modes of TDM, demultiplexing, signaling formats, and analog to digital conversion. Question and answer time. Let's see here. Hensley, what are the 3 steps of PCM? Hensley?
Quantize?
That's one of the steps, yeah.
Okay, so step 1 sample, step 2 quantize, and step 3 encode.
Excellent. Excellent. So, let's see here. Rodriguez, what are the 3 self-clocking signaling formats? Rodriguez?
Yes, sir. I'm trying to remember.
Well, you don't have to, you know. If you don't know, you don't know.
Was Synchronous one of them? I don't really remember.
Okay. No, Synchronous isn't one of them. Airman Moran, excuse me. 3 self-clocking signaling formats. Moran?
One of them is, I think it's CDI, right?
Correct. 2 more. Wish I could hear you, Mitchell. I got you maxed.
No, I'm sorry, sir. I'm just kind of clicking it. I know the answers. I didn't know if we wanted to wait, though.
Okay. Moran, do you know the other 2?
I don't know the rest.
Okay, well,
I
Mitchell,
think 0,
go ahead.
I don't know.
RZ polar and BZS, or bipolar. RZ bipolar with 0 suppression.
That is correct. Those are the other 2. So, Lawhorn, what makes CDI so much more different than the other signaling formats? Lawhorn? Oh, crap. Why don't you put it in the chat? Because I can barely, you know, I do not understand a word you said. All right, throwing it out there. Anybody? Okay, Lawhorn's going to write. Hang on just a sec. What makes CDI so much more different than the other signaling formats? One word? That's good. That's what I was looking for. Transitions. It doesn't care about it being going to a positive 5 for logic 1. It worries about the transitions. Good, good. At least you're listening. Thank you. All right. So we've covered 1 alpha and 1 bravo. Let's go to 1 Charlie. So we're going to be looking at identify basic facts about network bandwidth management equipment. The AFSC application says, hey, you're going to have to deal with bandwidth. When we were working with the FCC 100, yes, we had to be told what the bandwidth we were allowed and how to program, not how to program, but to program the cards and how much each one of them were allowed a specific bandwidth. So you have bandwidth allocations, network infrastructure, transmission media, carrier system concepts, and hierarchy. First one, there are 4 types of bandwidth allocation. There is conventional, demand assigned, dynamic, and time of day. Let's look at each one of them. Conventional, that's where you have the fixed amount. Look at that bottom line there. It says bandwidth is wasted if you're not using it. Here is an example of how the bandwidth is divided. You'll see that we have 4 channels, grand total of 256. The bandwidth is always going to have 256 regardless if you're using it or not. Next one is called demand assign. Now this one is very easy to understand why it's the internet. Everybody has an exact amount. However, if someone's not using theirs or if there's more allocated, and depending on the traffic, you can use it. Let's take a look at this. You can see that we've got the first 3 channels. First one has 64K, the other one has 9.6, the other one has 56K, and you still have 126.4 left out of that 256K. So what does that mean? Well, it means that if you are going to play some high-tech game and your particular internet company allows you to go more as far as your bandwidth, there will be a point where they are authorized to throttle you back. Hear that word? Throttle? Because if anybody exceeds their bandwidth for any length of time, and let's just say that you pay for, in my case, I think it's 25 down and 5 up or something to that extent. I get those 2 numbers mixed up, and that's what AT&T gives me here. Well, if I exceed that, like I'm playing my World of Tanks at times, there's a very good chance that I could get throttled back. And what would happen is, luckily, I dictate the bandwidth, so my 2 kids won't have any if I'm playing, if they decide to throttle me back. The advantages of understanding how the internet works to a certain degree. Next up, we have dynamic. Now this one is hoping, it's kind of like the trunking system. And the trunking system works off of, hey, I got, let's say, 10 frequencies. I've got 5,000 people on the base that have radios. The chances of all 5,000 wanting to get on the line at the same time are very slim. So the idea behind dynamic is to, just, yeah, they'll exceed everything, but the chances of you saturating it are slim. So when you see this, the dynamic, these are what's all assigned. You can see 384, it exceeds the bandpass or the bandwidth of 256. Yeah, we're going to have some issues there. There may be some issues with the timing. Everybody will be slowed down at that point. Next up, we have time of day restriction. The easiest way that I can remember in describing this is if anybody has ever seen The Lone Survivor, there's a couple times where they get out there and they try to make comm with back to the base with their SATCOM. Well, they're unable to, which I refer to the time of day restriction because they needed to call between a certain time each day. That's that time of day restriction. They have priority. No one else does. So they give you this particular time frame so you can make that call back. If you don't make that call, then oh boy, you're in trouble. Not really, but you just wasted some space there. Next up, we change gears and go into network infrastructure. Network being two or more users interchanging voice data, message traffic, and this is where everything gets crazy as far as network is concerned. You can be an intranet, you can be an internet. I have both. I have my cameras, I have my the other stuff that I can access that no one else can because it's blocked, but I also have the intranet. Now, with network infrastructure, there's a good reason why we started developing these electronic industry agency standards is because you want something called interoperability. You do not want to have what we had back in the, let's say, the late 80s and early 90s where you wanted, for example, Apple started dominating. Why? Because they seemed to have the better product during that time frame. They had a colored monitor. You could do a lot more with it. And PCs were just coming out at that time. But the problem is you had companies like Hewlett-Packard, Compaq, Dell, Brother, all these other agencies wanting to get in. But the problem that you had is you couldn't have let's just say a compact computer and a Dell printer. They wouldn't work. There was no interoperability with it. So by coming out with the EIA standards, they said, hey, this is how everything is going to work. Now the companies could, nice. Now the companies could let or have a standard in which everything can operate. So now you can operate your your Apple computer with a HP printer. That's interoperability right there. You got an Android phone that can talk to an iPhone, and vice versa. So we're going to look at EIA 232 Charlie and the EIA 530. EIA 232, I have bad memories of it, and some of you probably have come across this. Remember the old 56K internet where you had to do dial-up? Anybody remember that?
Yes, sir.
Okay.
Yes, sir.
Yeah. You remember that? Do-do-do-do-do-do. Bing. Yeah, they still have that on the you can go to YouTube and type that in and get that same tone. Well, anyway, this is pretty much the first part of how everything started working. Now we go into something how they're able to get your signal from point A to point B. They had two different types of transmission media, which was balanced lines and unbalanced lines. Now the first one we look at is balanced lines. Now what happened here is they're using a twisted pair. You're putting two signals on it. It's the same signal, but you're dividing it into two. But one of those signals will be 180 degrees out of phase from the other one. So when you go down the line, now please understand that when you go a distance on twisted pair, there's probably going to be noise on them. And with that, when it gets to the distant end, by putting both signals back into phase, you're able to cancel out the noise. This is the precursor to noise canceling headphones. Why? Because they take the noise from the outside and listen to the noise on the inside of your earpiece. And again, they flip it 180 degrees out of phase, so when they put it back into phase, it cancels it out. That's how noise canceling headphones work now. Again, this is on a twisted pair. When we go to unbalanced line, the data is being transmitted only on the one single conductor. The shield, that's the coax part, the shield is grounded. And that's to prevent noise and anything else interfering on the one line. So you have twisted pair for balanced, unbalanced you have coax. we have something called the EIA. Try that again. The EIA physical characteristics. Now, with this in mind, again, back in the day, we had 9-pin printers. What was it? Well, it's a D connector. You guys are going to be playing with D connectors when you're connecting the HHT 3000 to the back of the NSM 50. Those are D connectors. They're still used today. For those of you that have big computers, you either have a display port or a VGA or a digital VGA port. Normally the VGA port is a D connector. Now, if you have one of the, the government computers that they issued to you because you didn't want to use yours, it has I think a 25-pin D connector on it, and you can connect it up to an external monitor. That's one way to do it. Nowadays, with the newer computers, all they have is the Type-C. They do have HDMIs. They got a USB port, but nothing that can connect to a D connector. How technology has changed. We still operate our gear on these D connectors, and I think the D connector that you connect to the NRZ port is a 50 pair or a 50-pin D connector. This particular slide here is showing you that there is a very good possibility that you might run into something called negative logic. I've run into it before. The OJ314 was considered a negative logic console. The OJ314 is the air traffic control console back in the late 80s, early 90s, and they started getting replaced back in, I want to say, like 2005 to 2010. Most have been replaced, but you could still see these pop up on occasion. Let's go to the EIA 530. Now, this one is to take the place of the EIA 232 Charlie. Why? Because it can go faster. Now, you will be dealing with an EIA 530 on the NSM. You'll see it on the back of the case. It'll say EIA 530. There's also some others in there like 613, I think, but there's a couple others. Next one, we have something called data terminal equipment and data communications equipment. So in your study guide workbook, it does go into it. However, if you look at the slide, it makes it so much more simpler. It has a picture and a device. So if you got a device, and this is DTE, it's data terminal equipment. It is the source or the destination. So if you have a computer and you're going to send an email to someone, across the nation here, your computer is the source, and that computer on the distant end is the destination. That's considered a DTE. When you're working with the HST 3000 tomorrow, it's also classified as a DTE. Next up, we have a data communication equipment, DCE. Notice how DTE and DCE sound the same. This particular one you can classify as a modem. I like a modem better than I like the router and all the other stuff. Why? The modem converts everything over to an actual AC signal as opposed to a DC signal. AC goes farther than DC. Now, with this one, it says device that establishes, maintains, and ends a data transfer. Data transfer being when you transmit the ones and zeros out of the computer, it gets modulated in a modem and sends it to wherever the next place it needs to go to. It demodulates it, and it gives the ones and zeros to the computer. There are 4 different types of transmission media. We got twisted pair, coax, fiber optic, and wireless. Let's look at each one of them. Twisted pair is pretty easy to understand. This is a balanced line, and pretty much, the faster you want it to go, the more twisted you've got to get it. That's the difference between Cat 5 and Cat 6. Next up, we have coax cable. This one, the thicker the cable, or the thicker that center pin is, the conductor, the better it's going to handle the traffic on it. Also, RG6 comes in a couple different flavors. You can have what's called a dual shield or a triple shield, and in some cases a quad shield. What does that mean? It means there's, a quad shield is 4 different shields on the outer coat of it to prevent any information from the outside getting in. Of course, it also has to be grounded too. If it is not grounded, then there's a very good chance that you're going to see some signal issues with it. Unbalanced line. We got fiber optic. This is light. Were you aware that light is a form of RF? Interesting. It's in the terahertz. Each color has its own wavelength. And this is how we're able to modulate this and send it to the distant end. You can put a lot of information on it. This is what everybody's going to through the phone and TV. But there are places that do not have it. My mom, who lives in the rural area of Kentucky, has fiber. Me in the city here, I don't have fiber yet. They've been telling me for the last 3 years I was going to have fiber. Still waiting. Again, fiber is the way to go. Next up is wireless. This one, obvious, transmit and receives without the use of wires. Gives you a couple different scenarios: line of sight, satellite, tropo, Wi-Fi, Bluetooth. Yeah, increasingly popular. Well, yeah, if you don't have to carry a cable around all the time, you're tethered to something. A lot of people don't like that. Next up, we have something with carrier system concepts. This is where we see some confusion. Try that again. Some confusion when you are doing your studying. The easiest way is to take a look at this picture. You will see that we have a LAN set up with a router, and then it goes to a DSU. DSU looks at the customer side of the network. Customer side, the user, the computers that's in, let's say, your business or the dorm there. DSU. It is considered alternate mark inversion, better known as RZ bipolar. It is not self-clocking. Let's try to decipher what I'm getting at. If you were to have problems with your internet, talking outside the gate here, you're in a residence like I am, and you have problems with your internet, and you call them up and say, hey, I got problems with my internet. Well, they're going to do a couple checks to see if it's on your side. So they're going to use the DSU and do a loopback to see if everything is working on your end. If they can't find anything on that, they'll do something called the channel service unit, and we'll look at the network side. This one uses RZ bipolar with zero suppression, self-clocking. Again, CSU, channel service unit, is the network side. Network side. I get a lot of, well, CSU is the customer service unit, so that's on the customer side. No. Please don't get into that confusion area, okay? Channel service unit is the network side, and it is self-clocking. Next up, we have hierarchy. I think you guys had this in block 6. Yes, no, maybe?
No.
No? I thought you guys did it in block
It
6.
does not look familiar, sir.
Okay. All right, what this goes is they're building a logical transmission rate in a network. How do they do it? Well, first of all, they take one channel? Well, one channel is 64K. To get us into what's called a T1 or DS1 line, you got to put 24 channels in there, which ends up with a max data rate of 1.55 megabits per second. And there's ways to figure it out. We used to do it back in the FCC 100. To get a T2 line, that's when you start combining multiplexers. You're going to end up taking, I think, 4 multiplexers that are T1 and run them into one multiplexer, and out of that multiplexer is a grand total of 6.312 megabits per second. Start to see that the more you combine multiplexers, the quicker it starts to become. Then you got a DS3, which is a T3 line. I can't remember how many it is, but let's look at the next one here, which gives us an idea how we're building these multiplexers. So when we have a T3 line, we have 7 T2 multiplexers coming into it. When it comes out, it's a T3. To get a T4 line, you got to have 6 of the T3 multiplexers to get a T4 out. You can see as it keeps going, it increases. However, when you get past the 4, from what I understand, you start developing what's called superscripts, which are errors. And they create problems when you start going to a T5. Depends on your equipment and how well it is working with the hierarchy. So that's what hierarchy is. So we've gone through bandwidth allocations, network infrastructure, transmission, media, carrier system concepts, and hierarchy. Any questions?
No, sir.
All right. Questions? We'll go to the next one. 1 delta. We're going to look at identify basic facts about principles, capabilities, limitations of multiplexing equipment. Just remember, you got to get 28 out of 40 correct on the test to pass. Again, it's a pretty tough test. Is anybody out there taking college courses online?
I have, sir.
Yes, sir.
Okay. This test resembles probably a sophomore or junior in college. It's a pretty tough test and relies a lot on you to logically figure out the answer. Again, the FSC application means that you're going to be working on the NSM 50, which is a nodal satellite multiplexer. So we look at the NSM, purpose, functional description, operational characteristics, the NSM configuration. So let's go through each one. The purpose, and I'm not going to stay very long on these slides because we're going to go over the actual tech order where I show you where all of this is at. When you are taking the test, the NSM tech manual is allowed and be given to you. Again, it'll be on a disk for you guys to load to your computer. Now the max output of this, and I'm going to show you on the tech order, is 52 megabits per second. It has 2 operational modes, legacy and enhanced. What does that mean? Legacy meaning me, the old fart, and enhanced meaning you, the young guys and gals. When they say selectable via NSM configuration cut sheet, yes, you're going to be given a cut sheet and you're going to have to input it in on the computer through what's called a GUI, Graphical User Interface Program. Here are the input ports and max data rates. Again, we'll go through the tech manual for it at the end of, I think, 2 alpha. This is what it looks like on the back of the case. Now, if you can look right above my head here, you will see an iDirect modem immediately after the 338. But the 3 cases that are above that, the one on the far left is the NSM case. On the back of that case is where you're going to be putting the connector from the HST 3000s on the D connectors in the red. That's the NRZ ports. And of course, we're going to refer to this manual here real quick. We'll get back to this in just a minute. You can see that it's going to interconnect with the TSC 179. Those are the other 2 cases that you see off to the right. So we'll get to this in just a minute as soon as we go through 2 alpha. We're going to look at identify basic facts and capabilities about the limitations of the bit error rate test set, BERTS, not Bert and Ernie. Again, you got to get 28 out of 40 in order to pass. You might have to use a BERT. In fact, in Block 9, you're going to be using the BERTs, better known as the HST 3000s. Let's take a look at it. We're going to describe it, look at the HST 3000, and go from there. This is what it does. You can see that it performs tests, loopbacks on a system to adequately analyze signal quality as it travels across the network, alone or alongside the mission traffic. What does that mean? It means that you can get to check all those signals and figure out if you've got errors in the mission data stream. Now, the BERTs that you guys are going to be using is called the HST 3000. This is considered a datacom module. So if you see anything that relates to the datacom, you need to reference everything to the HST 3000. You can see it does end-to-end testing, the bit error rate test. It does 3, count them, 3 test modes. Oh gee, you've seen DTE emulation. You've seen DCE emulation. But you didn't see monitor. Monitors where you get to see what's going on alongside that mission traffic. So those are 3 test modes. If you were, we do not provide you the Datacom tech manual with it because it's very large. And also this, what we got up here on your study guide workbook is, that's it. That's all you really need to understand or know. So 3 test modes, DTE, DCE emulation, and monitor. Any questions? Because we've gone over all the information we need to go over until we get to this one. So everybody pull up their operator's instruction manual for the NSM Nodal Satellite Multiplexer. And I think it is considered the 31R2-2 TSC 179-2 extract NSM50's operator manual PDF file. I'll wait till you guys get to it and pull it up.
Sir, does that mean we'll have TOs on the test?
That is correct. You'll get the NSM TO or tech manual, and you'll get the Jerk 239 tech order. It also comes with the electronic C's and D's, but there's paper C's and D's if you want to use those.
Sir, is the test going to be majority TO questions, or is it like mixed with the study guide workbook information?
Let me see how I can word this without compromising. Let's just say that you've got probably 5-6 questions on the NSM and about 5 to 7 questions on the TISR, which is a Jerk 239.
Thank you, sir.
So about a fourth of your test is coming from tech manual or tech orders. But I can guarantee you, if you miss a tech order or a tech manual question, they're going to, yeah, why? And right now, I'll tell you, if you're not familiar with the tech manual or tech order, you're going to miss it. You will miss it. So Control F. There's places in there, if you don't know what to ask it, you're going to be looking, because it'll have like 2,000, that you're going to have to look at. So hopefully I'll be able to narrow it down enough for you to go, okay, I need to focus here and here when it's asking a question. Everybody got it? Who doesn't have this pulled up yet? All right, I'm going to assume that you guys got it, so let's go through it. This is a Vertex RSI, is the company, coming out of Longview, Texas. Scan down here to the first thing. There we go. This is the introduction. This tells you a little bit about it. Lightweight synchronous. Wow, have you heard that term? Time division multiplexer. Heard that term before, eh? Provides both aggregate interfaces to satellite modems and group interfaces to ground equipment. So it is the go-between the modem and the ground equipment. That was the next part we need to look at is in 1.3. This is a general function of it, this whole paragraph. Even though that we just went through part of it on the slideshow, it just goes to show you how much more information is in there. The big thing here that you can take out of is whatever it does in the multiplex mode, it will do in the demultiplex mode. About halfway down the paragraph, you'll see it says M and C, Mike, and the little at symbol. Not at symbol, it's I don't know. I call it an at symbol, but it's not an app. Ooh, we lost somebody. It's not an at symbol. I can't remember the name. Thank you. Ampersand. Mike and Charlie can be accessed either directly using the Mike and Charlie protocol or through the GUI software. This is what you're going to be using tomorrow, is the GUI software. So you're going to program the NSM what to do. And of course it goes through what it is, what temp it's operating as. And this is all in chapter 1. 1.3.1.4 control computer interface. This is basically what you're doing. You'll notice it says RS-232 or 422 DTE signals. Wow. Data terminal equipment. In other words, it acts like the computer, using the computer. Wow. All right. Here's where some key ingredients are in chapter 1. 1.3.1.5 external signal interface descriptions. Anything and everything you wanted to know about the rear of that NSM and its connectors. You can see Bravo showing you that you have an NRZ group port. It's in balanced. Ooh, balanced 422. You have legacy. Wow, we lost Sergeant Grove there. Wow, he's back. So we have legacy and enhanced. Now, with that in mind, legacy being the old, enhanced being the new equipment, you can see that I've got highlighted that the enhanced mode is where you want to go for max data rate. So if I asked you, hey, in legacy mode, what's the max data rate? What should be the answer? Anybody?
1152
That
kilobytes
is
per second.
correct. Now, if I ask you, what is the max data rate of the NRZ group port, what should you say?
Is it still 1152 in legacy mode, the NRZ group port?
Negative. I'm asking for the max data rate of the NRZ port. This is a hint, ladies and gentlemen. If it's a max data rate for the port, you go looking for the max data rate of everything. In our case, always go to the enhanced because it's a newer equipment and it's going to be faster. So on enhanced, which is number 2, you'll see 8448 kilobits per second or 8.448 megabits per second. So that's what you're looking for. So if it says max data rate for an NRZ port, look for the highest data rate. You look at Charlie, T1, E1 group ports must be bipolar. Okay. I can tell you that the T1 line, which is number 1, or B, Bravo 8, Zulu Sierra, that is bipolar with zero suppression, it has a frequency of 1.544 megabits per second. Notice I changed it. It still reads the same. And the E1 port is alternate mark inversion or Hotel Delta Bravo 3 at a frequency of 2048. Now let me explain those two. The T1, which is the Bravo 8 Zulu Sierra, is a North American T1 line. With E1, the HD, the Hotel Delta Bravo 3, it is a European or Japanese line. So you can use this equipment overseas. Delta, which is group modem, better known as CDI, you have two different standards, which is legacy and enhanced, so you can operate the old equipment with the new equipment. You have Echo, which is the history, is what I like to call it. Notice it says EIA 530 or EIA 613, the newer one, in one of the following frequencies. You can see number 3 is where we got the max data rate from the TISR, or the NSM. So 52 meg or 52,000 kilobits per second. You can see that F says secure order wire. I'm going to caution you ahead of time. You're going to see order wire pop up on occasion a lot in the TISR. What does that mean? Order wire is our own channel. It is separate from the mission traffic. In other words, it's ours. Why? Because we need it to troubleshoot back and forth. So keeping a separate line is the reason for that. You'll notice it says must be unbalanced NRZ. In other words, it's on a B and C cable. So that's the first part of where you can find all the data rates and what ports they go to. This is what the equipment looks like. The peripheral equipment is a tough book that you'll be running. It is connected. We have the theory of operation. And remember that first slide we had the purpose? Right there it is on 2.2. And I love figure 2-1. It gives a simplistic way of showing you how everything works with the NSM. So all the people coming into the NSM, that's your multiplexer, goes to the satellite modem. Modem sends it up to, using the SATCOM frequencies, to the bird. The bird repeats it back down to the other end, and then it demodulates it, sends it to the multiplexer. It demultiplexes and sends it out to the users or channels. Here's a functional description, and I thought this was kind of eye-opening. you'll see it in the descriptions below. MUX refers to multiplexer. DMUX refers to demultiplexing. Yep, some people need to have it explained. So if you really wanted to know about how many ports there, picture's worth 1,000 words. Right there that is. You can't miss it. And this is figure 2-2. Notice in chapter 1 is where all the ports and the speeds are, and chapter 2 tells you how many ports there is. I like to point this out because of the network configurations. It's probably one of the best ones I've seen in quite some time. Here is your user port interfaces telling you how many there is. You can see the NRZ is a 530, has 12 balanced. You've got the next one, which is bipolar, which is a T1E1. Those are 6 of those. You got CDI, which is your group modem. There's 6 of those. And then the HISI has 2 of them. This is where order wire comes into play. Again, it's our channel to do. Mainly for making sure we got connections and to verify that things are working according to the way they're supposed to be working. This is the installation. This is the rear. And it doesn't look anything like the back of the case. That's because the case is what is separated out where it's easier to access than if you were to try to connect everything back on the back panel, because you would have to separate everything out anyway, and it'd be a lot of wires back there. So what they did is you can see that J2 and J3, you can see that it's one socket for J2 and one socket for J3. You can see where they get separated out on the rear of that case. One socket controls 1 through 6 and the other socket controls 6 through 12. Has everything to do with wiring and everything else. This is an off-the-shelf item too, if you wanted to know. This is the front panel, the NSM. It's on the very top. If you were to look at the front case, it comes with, looks like about 7 different types of LEDs. Just remember number 5. When you are programming, number 5 is the key. If you've completed your programming and you've cleared all of your alarms in that, there's a decent probability that number 5 will still be illuminated, and that's not good. Number 5 is an error LED telling you you've either didn't put your NSM in the right spot or you didn't have your HST doing what it was supposed to be doing. So it could have an error for that. And 3-3 shows you the NSM icon that you're going to be clicking on when you get to the computer and open it up. Down here, the next one, it starts to show you the, it's a very unclear picture here, but it gives you an idea of what you're going to be doing as far as selecting. It's going to come up with these windows. You're going to go through the tabs and put everything in that you need to put in. And that pretty much wraps it up. Is there anything out there that you guys want to ask? No? Maybe?
Sir,
Go ahead.
would you suggest studying the definitions of everything we've gone over today?
I suggest studying the definitions that we've gone over today, yeah. I would do that. Mainly to keep things straight. Just remember, we have other items that are in there that we went over. You know, like what are the 4 types of network synchronization? What are they? Anybody? Huh? Things like plesiochronous, mutual, master clock, master slave. So identify those. when you look at the objectives, it says identify or list or things like that. That's what we're looking for. We're looking for generalities. We're not looking to get complicated, but even though we explain it, to give you an idea how, let's say, self-clocking, what are the 3 self-clocking signaling formats out there? What are the 3 steps of PCM? What does rounding do? How do I correct it? Things like that. That make a little bit more sense there, Airman Smith?
Yes, sir.
Okay. So there's a lot of information here. Your head's probably swimming by now. Tomorrow at
Yes.
yeah, I know. I was that way when I stepped into the block, and then I had literally had to put forth a lot of effort because I was behind this stuff. I wasn't ahead of it. And then I got good at it once I started figuring things out. So hopefully it'll come to you one of these days. But this is to get you introduced into what is out there and what you might have to troubleshoot and repair or set up. Yeah, there's a lot here. All right, tomorrow morning, 9 o'clock, is homework. Make sure you have it completed. We'll go over it. I'll ask you to hand it in. You can take like pictures of it if you did it by hand and send it in that way. You can do either Word or Notepad. I've even had Google Docs handed in, as long as you're handing in everything. So with that in mind, is there any other questions?